All right, welcome. Today, we are going to demystify one of the most fundamental tools in all of data science, linear regression. Now, it might sound a little intimidating, but I promise you, it's all about a really simple human idea, finding a clear, straight line through a messy world of data. By the end of this, you'll see exactly how this one idea powers everything from predicting stock prices to understanding scientific results. So let's get into it. So here's our game plan. We're going to break this down into 5 simple parts. We'll start with a basic prediction problem, then we'll figure out what it means to draw the best line through our data. After that, we'll see how a model even knows what best is by measuring its own errors. Then, we'll get our hands dirty and put the theory into practice. And finally, we'll decode what our model actually learned. Okay, so to make this feel real, we are not going to start with a bunch of abstract math equations. Nope. We're going to start with something a little more beautiful. Flowers. We'll be using the famous iris dataset to ground this whole thing in something we can actually see and understand.
So here's the central puzzle we're trying to solve. Imagine you know a flower's sepal width, its petal length, and its petal width. With just that information, could you make a really good guess about its sepal length? This is exactly the kind of question that linear regression was born to answer.
To solve our little flower problem, we need the right tool. And that tool is all about one core mission, finding the single best possible straight line that can cut right through the heart of our data points. So, what is linear regression when you strip it all down? At its core, it's a way to model a relationship. It looks at all our data, all those different flower measurements, and it draws the one line that best represents the overall trend. It's kind of like finding the perfect average slope through a scattered cloud of points, which gives us a surprisingly powerful way to make predictions. I love this slide because it breaks down the prediction into something like a recipe. First, you have your starting point, your baseline. We call that the intercept. Then, you start adding your ingredients, your features, like petal length. But you don't add them all equally, each one is weighted by how important it is. And finally, you have to account for a little bit of noise, the random chaos of the real world that means our predictions will never be 100% perfect. Okay, so I've been throwing around this term best line, but that's pretty vague. How does a machine, a piece of code, actually define what best is? This is where we get into the really crucial idea of measuring mistakes, or what we call error.
This is the key question, right? The model doesn't have gut feelings or intuition. It needs a cold, hard mathematical way to score itself. So what it does is it tries out tons of different lines, and for every single one, it calculates a mistake score. The line that ends up with the absolute lowest score, well, that's our winner. That's the best fit.
Now, there are a few ways to score these mistakes. On the right, you've got mean absolute error, or MAE. It's simple. It just averages the raw distance of each point from the line. A miss by 1 centimeter is just a 1-point penalty. But on the left, we have the much more common method, mean squared error, or MSE. By squaring the errors, it punishes big mistakes way more than small ones. A miss by 2 centimeters isn't a penalty of 2, it's a penalty of 4. This forces the model to pay extra attention to those really bad guesses. Plus, and this is a big reason we use it, the math of finding the lowest point on a smooth, squared curve is just much easier for a computer to handle. So here's the bottom line. The entire goal of this linear regression algorithm is to hunt for the one, unique line, the specific starting point and the specific weights for each feature that makes this mean squared error value as small as it is mathematically possible to be. That's the whole game. All right, that's enough theory for now. Let's see how all this stuff actually comes together when we write some code. We're going to walk through the most important steps for building our flower prediction model. The very first thing we have to do, and this is absolutely non-negotiable, is split our data. We use one part, the training set, to actually teach the model. Then we hide the other part, the testing set, and use it later to get a fair grade on how well the model learned. This is so important because it stops the model from just memorizing the answers instead of learning the actual patterns. Next up is scaling. Think about it. Petal length and sepal width could have totally different ranges of values. By scaling them, we put all our features onto the same common scale. This is super important because it allows us to fairly compare their final coefficients to see which feature truly has the biggest impact on our prediction. And here it is. This is the magic moment.
This one line of code is where all the learning actually happens. When we call model.fit, we're basically telling the algorithm, okay, look at all this training data and use the ordinary least squares method to figure out the one single line that minimizes the mean squared error. And just like that, in that one command, our model is born.
So once the model is fit, once it's been trained, it's ready to go to work. We can now give it our hidden test data, the stuff it has never ever seen before, and ask it to make its best guess for the sepal length of each of those new flowers. So we've built the model, but our job is not done. In fact, maybe the most important part is understanding what it actually learned. It's time to open up that black box and see what's really going on inside.
And this is what the model figured out. These numbers are the coefficients, the weights or importance scores it learned for each feature. And you can see right away, the model found a massive positive relationship for petal length. This means as the petal length goes up, the model strongly predicts the sepal length will go up too. On the other hand, it found a small negative relationship for sepal width. The size of that number tells us just how strong the influence is.
So, how good is our model overall? We can use a metric called R-squared. A score of about 0.85 is fantastic. It means that our model, just using those few measurements, can explain roughly 85% of all the variation we see in sepal lengths. That is a really strong and reliable result. Just to make this crystal clear, if a feature had a coefficient of 0.5, it would literally mean that for every 1 centimeter increase in that feature, our model predicts a ½ centimeter increase in the sepal length, assuming all the other features stay the same. It's that direct, that simple to interpret.
And that brings us to our final thought. We've built a model with a great R-squared score, which is awesome. But that's not the whole story. What if the real-world relationship isn't a perfect straight line? What if there are hidden problems in our data? This question leads us perfectly into the deeper world of model evaluation.